Excuse me. All right. I hope you guys are doing well this afternoon. Today we are going to talk about complex numbers. And a large part of what we're going to talk about today, I am actually truly expecting you guys to do 99% of this on your calculators. So I've taken the time to download some calculator emulators so that we can, or I can show you how to use your calculators to do some of this math. So let's go ahead and get cracking. So what I'm going to put in the middle of the page here is a representation of a complex plane. So we're going to have some vertical axis, and then we will also have a horizontal axis like so. A complex number is a number that contains both a real part and an imaginary part. So the real part is going to be where we put things on the horizontal axis. So think about this as just a number line going from negative infinity if we go all the way to the left, out to positive infinity if we go all the way out to the right. Just a number line like you guys dealt with in elementary school and all of that kind of good stuff. And then our vertical axis is another number line, but it represents imaginary numbers, where a imaginary negative infinity is all the way at the bottom, and a positive imaginary infinity is all the way at the top. So there are lots of different ways. I say lots, there are really just three different ways that we can choose to represent a complex number. And we're going to talk about those different ways and how to convert back and forth between them and all of that kind of good stuff here before we get into doing any real mathematical operations with them. So first, I want to introduce rectangular form complex numbers. So a rectangular form complex number is usually of the form as follows. So my complex number, I'm going to call it A, and I'm going to put a bar over it, and that's going to tell you guys that you're dealing with a complex number. In textbooks and stuff like that, you might see complex numbers represented by bold-faced letters, but because I can't write in bold, this is the way that I'm going to use to distinguish a complex number. So anyway, so we have complex number A, and it will have a real part, lowercase a, and then an imaginary part, lowercase b. And we're going to use the imaginary operator, j, to tell us which part is the imaginary part. So before we move on from this bit right here, I want to define our imaginary operator j really quickly. So j is literally just the same thing as the imaginary number I, which is simply the square root of -1. We use j in electrical engineering because we use I to represent current so often that that would be confusing. So just to be really clear here, the real part of complex number A is lowercase a, and the imaginary part of complex number A is lowercase b. So if we wanted to represent this rectangular form complex number on our complex plane, we would go out a units in the real direction and up b units in the imaginary direction, and that would give us the following complex number. Like so. So you can treat a rectangular form complex number like a two-dimensional vector, where the real part tells you how many units to go in the x direction, and the imaginary part tells you how many units to go in the y direction. Okay. So any questions about rectangular form complex numbers before we move on to exponential form complex numbers? And if you have any questions, please ask, because we're going to be using these weird new numbers for the rest of the class. So it's very fundamentally important that you guys understand what's going on here.
Are we going to go into 3 dimensions?
So there is no third dimension for a complex number. It is just a 2D representation. So you bring up an important thing here. I'm going to talk about it a little bit more in a bit. So this is a 2-dimensional vector. And so that means that there are certain vector operations like cross product, dot product, and stuff like that that we actually can't do with these. So when I define our mathematical operations, I'm going to make some notes about things, because some of the symbols that are used with complex numbers can be easily confused with vector operations. So I'm going to try to be as clear as I possibly can on that end. Any other questions before we move on to our next way to represent a complex number? All right. So next we're going to talk about exponential complex numbers. Okay. So in an exponential form complex number, I'm going to have something like this. So A is going to be equal to some magnitude or length of our vector A, e to the j theta A. Okay. So that length vector, let me do it like this, is simply the length, and then theta A is simply the angle formed between the positive real axis and our complex number. So in an exponential form, we don't have a real part and an imaginary part. We have a length and an angle. Okay. Now, there's also another way to represent complex numbers, polar form. And the polar form is just a shorthand notation for the exponential form. So a polar form complex number might look like this, where we have our magnitude and then an angle operator and then theta A. So it contains the exact same information as our exponential form complex number, but it's a little easier to write down because it doesn't have that e to the j bit. That's replaced by the angle operator right here. Now, as it happens, your calculators can only handle rectangular form complex numbers and polar form complex numbers. So anytime you're given an exponential form complex number, you're expected to be able to input that into your calculator as a polar form complex number. And you do that simply by keeping the magnitude, keeping the angle, and then throwing everything else away. All right, so let's talk about switching back and forth between these things, okay? So if we had a rectangular form complex number and we wanted to figure out the magnitude of that complex number, well, the magnitude of complex number A, we can get simply by doing effectively the Pythagorean theorem, right? So if we look at our little complex number A, it forms a right triangle, right? And the length is just the hypotenuse of that right triangle. So it's just going to be the square root of a squared plus b squared, which we could write more generally as the square root of the real part of complex number a squared plus the imaginary part of complex number a squared. Using trig identities, we can figure out what our angle theta a is going to be. And we're going to use the relationship, the inverse tangent of b over a, which in more general form is the inverse tangent of the imaginary part of complex number a divided by the real part of complex number a. So these are the two relationships that we would use if we had a rectangular form complex number and wanted to convert it into either an exponential form complex number or a polar form complex number. Okay. There are some nuances to this that we'll discuss here in a moment. But before we work an example problem, I want to cover how to go from exponential or polar back into rectangular as well. So in terms of magnitude and angle, the real part a, the real part of complex number uppercase a would be lowercase a, and that is the magnitude of a cosine our angle, and b is just going to be the magnitude of a sine our angle. All right, so before we work an example here, does anybody have any questions? All right, so I'm just going to give you fair warning that the example that I'm about to work is intended to break these relationships, and it will actually illustrate to you the importance of having a good calculator for the remainder of this class. Okay, so let's say that I have a complex number x, and it is -3 plus j4. And we want to convert this into polar form. That means that our expected result would be of the form magnitude x, angle theta x, like so. Okay. So if I use the relationships that we just defined, the magnitude of x would be what? Somebody tell me what I should put in my equation here, please.
Square root of 3 squared plus 4 squared.
So just to be granular here, I'm going to do -3 squared. I know that there is no difference between -3 squared and +3 squared, but I'm about to illustrate a point. That's why it's important, but you're correct. Plus 4 squared. And I intentionally did this because it's a simple 3, 4, 5 triangle. So this is going to come out to be 5 because 16 plus 9 is 25, square root of 25 is 5. So that bit's fairly straightforward. Now let's figure out theta x, right? So using the equation, we should have the inverse tangent of 4 over -3. I would like for you guys to throw that into your calculator and tell me what you get so that I can prove I'm not doing anything facetious or tricky here.
I got negative 53.13.
Negative 53.13. That should obviously be in degrees because radians only goes up to 6.28 or so. All right, so thank you for that. So I know that we used the equations that I just gave you, but our answer here is technically wrong. Before I draw a picture, does anybody have any idea what's wrong?
The reference of the angle.
Right. So if I were to plot complex number x on a complex plane, which is exactly what I'm going to do here. So here's my real axis. Here's my imaginary axis. So I'm going to go -3 units in the real direction, and then +4 units in the up direction. So this, sorry, I shouldn't put those absolute value signs around it because I'm not dealing with a magnitude. So this is x as was defined by our rectangular coordinates, right? We went to the left, -3 units, and up, +4 units. Well, according to my polar or exponential coordinates, I should go 5 units out. So that would be something like this, and then swing down until I hit an angle of -53.13 degrees, which would be, let's see, so here would be 45, so somewhere in the ballpark of here. So this is the x that I'm getting from my polar or exponential coordinates. And it appears to be, and it actually is, exactly 180 degrees away from what our rectangular coordinates tell us it should be. Can anybody think of the reason why that might be the case?
It's the negative sign on the 3.
Exactly right. So your calculator literally cannot tell the difference between the inverse tangent of -4 over +3, -3, when you use the arctangent operation. The arctangent operation will always return an angle that is either in the first quadrant, so that's one up here on the top left, or the fourth quadrant, which is this one that's down here on the bottom right. So realistically, we could get the correct answer if we simply added 180 degrees to this. So let's see, so 4 over -3 plus 180. So that would come out to be positive 126.8698. So let's call that 870 degrees. And 126.870 degrees seems like it should be about here because it's, you know, from here to here is 90 degrees and then a little bit more than 30 more. So that makes sense. So this is a problem for our hand calculations like we've done here. I mean, even though we used a calculator to do the inverse tangent thing, we're doing all of this manually. And it would be a huge pain in the butt if we had to constantly look at both the polar form representation and the rectangular form representation to make sure that we got the correct answer. But the calculators that I've suggested for this class, in particular, the TI-36X, the Casio 115, and the Casio 991, all have a mode that does this for us automatically. So that's what I want us to learn how to do next, is simply to use our calculator to convert between a rectangular form complex number and a polar form complex number, and vice versa. So I'm going to start with the TI. So hopefully you all can see a picture. It says it's a TI 30X Pro, but that's not true because the 30X is a peasant calculator that can't do most of the stuff that this one can. This is actually a 36. But anyway, can you guys all see the big calculator on your screen?
Yes, sir.
Okay. So all I'm going to do is I'm going to put in our complex number X. If I can find my mouse cursor, here we go. So that should be -3 plus, and in order for us to get to the imaginary operator, actually 4, and the imaginary operator, I press the pi button 3 times. So -3 plus 4i. Now I'm going to press second, and then that pi button again, and it's going to bring up a menu. And this is where all of the complex functions on a TI calculator live. So if we go down here, keep on going, option 4 here converts whatever we put in into polar form, and then option 5 converts whatever we put in into rectangular form. So these are this particular calculator's way of just automatically converting into polar form specifically or rectangular form specifically. So I'm going to press option 4 here and then enter, and it spits out 5 angle 126.8698 blah blah blah. So it got the magnitude right and the angle right without having to worry about whether or not we actually need to add 180 degrees or anything like that. Just to illustrate, if we wanted to convert that back into rectangular form, second complex, and then option 5, and it gives us the -3 plus 4i. For what it's worth, these TI calculators come set to give you answers in rectangular form by default. The majority of the time, we are going to be asked to express answers in polar form because polar form is what is traditionally used to express voltages and currents. So we can actually change our calculator settings by pressing mode, and then notice down here, this bottommost option, it says real, and then A plus BI, and then R angle theta. So this is where we can change our setting. To default express answers in polar form. And then I'll clear this out. And so now if we put in -3 plus 4i and just hit enter, it automatically gives us the result in polar form. All right, so Before I move on to our Casio users, do any of our TI users have a question about what we've just done? All right. So now I'm going to bring up this guy right here. So this is the Casio 991. This is actually the model that Casio discontinued sometime during this year, but some of you may have this. Hopefully you have real ones and not. There are some very good looking knockoffs that actually give math errors constantly when you try to use them for things. So if you bought one of these off of eBay for less than $20, it's almost assured that you have a crappy knockoff and you're going to have a hard time. But anyway, this. I want to also show. Oh, the keylog thing is right here. Great. Okay, so these Casio calculators are also very good and they can do everything that the TI calculators can. The reason why I like the Casio calculators a little bit less is because we actually have to fully switch the mode of our calculator. So the TI, we can just kind of do everything by using that complex menu. The Casios, we have to literally tell, hey, you're about to be dealing with complex numbers. So in order to do that, we press the menu button. And I do not know why this emulator does not have English as a language, but option 2 is for complex numbers. So I'm going to press 2, and now the calculator is in complex mode, which is designated by this I up here. And so I would type in -3 plus 4. And then if I press the engineering button, that's where my imaginary operator I is. In order to convert this rectangular form complex number into polar form, I press the option button, and this is where all of the complex number operations are. I don't know what language this is, so I'm getting my physical calculator here so I can read things off to you. So option 1 should be argument. That literally just returns the angle of a complex number. Option 2 is the conjugate. We'll talk about that as a complex number operation here in a couple of moments. Option 3 is real number. Option 4 is the imaginary part. If we scroll down, this is where we get our conversions. So option 1 converts to polar form, option 2 converts to rectangular form. So I'm going to press option 1 here after having scrolled down and press equal, and we get 5 angle 126.869, blah, blah, blah. If we wanted to set this type of calculator to have polar form complex numbers as the default, we would press Shift menu, go down to option 2, and now option 1 uses rectangular numbers as the default, option 2 uses polar form complex numbers as the default. So I'm going to press 2. And now this calculator is set to give me polar form complex numbers by default when it's in complex mode. Do any of my Casio 991 users have any questions? All right, so in order to show you guys how to use a Casio 115, which is the other most popular calculator in this class, I have to close this out because for whatever reason, the Casio emulators use the same files. So if you have a 115, this is the second edition, but it has the same button layout as those of you that have it. So we have to do effectively the same thing, press mode, and then option 2 for complex, -3 +4 engineering button. So the Casio 115 does not have the option button like the Casio 991 has. Instead, you press Shift 2 to bring up the complex menu. And the options on the Casio 115 are a little bit more limited. You can only do argument, conjugate, convert to polar form, and convert to rectangular form. There isn't an option that just gives you the real part or just gives you the imaginary part. So I'm going to choose option 3, press equal. We got the same answer as we've gotten every other time we've worked this. And for those of you interested in setting up your calculator to give you polar form complex numbers by default, we would press Shift, Mode, scroll down, option 3, and then option 2. Okay, so before we move along to operations and stuff like that, does anybody have any questions on their calculators? And I'm going to pre-apologize if any of you guys are using an HP 33S. I do not know how to use that calculator at all. At some point, I'll probably wind up buying one, but I usually only have like one student a year that has it, so I haven't invested the $25 yet. Okie dokie. So let's talk about mathematical operations. So the first operation that I want to talk about is the complex conjugate operation. And this operation is only applicable to complex numbers, okay? So you may see something like this. Actually, let me do it this way. So let's do in rectangular first here, okay? So if we have a complex number A is equal to A plus JB, the conjugate operation would look like complex number A and then an asterisk symbol, okay? For a rectangular form complex number, the conjugate operation is simply changing the sign on the imaginary part. So that would look like A minus JB. If we were to plot our complex number on our complex plane, if this is A, then this would be a conjugate. So it's going to be the exact same complex number, but it's just flipped over the horizontal axis. So from that, what do you think a conjugate is going to look like in polar form? So let me give you guys what I hope is a strong hint. So here is our magnitude. Here is our angle. If we were to flip that complex number A across the horizontal axis, would the magnitude or the length of that vector change?
It'd be negative theta.
Exactly right. So everything is exactly the same, except that we change the sign on the angle. Now, this isn't a particularly hard operation to figure out, but if for whatever reason you can't remember it or anything like that, your calculators can do the complex conjugate operation for you. Okay, put a conjugate symbol here, or that's confusing. Okay, so the conjugate operation simply changes the sign on the imaginary part for a rectangular form complex number and changes the sign on the angle for a polar or exponential form complex number. I just wrote polar form down because that's what our calculators handle. Any questions regarding the conjugate operation? All right. So I didn't write conjugate, so I'm going to move all of this stuff down just a smidge, and I apologize for this, and write up here conjugate. All right. My apologies. So now let's look at addition. So let's say that I have a complex number A is equal to lowercase a plus JB, and a complex number B is equal to C plus lowercase j, or excuse me, C plus JD. Okay. The addition operation would look something like this. So we would have A plus B would be equal to A plus JB plus C plus JD. And we would simply add the real parts together. So that's going to be A plus C. And then we add the imaginary parts together. So J, B plus D. So addition of complex numbers in rectangular form is literally the exact same thing as what you're used to doing with vector addition. So you add the x components together and then add the y components together, and you get your resultant complex number. Subtraction is literally just addition, except that there's a negative sign involved, right? So again, dealing with rectangular numbers, if we have a complex number A is equal to A plus JB, and a complex number B is equal to C plus JD, then the subtraction operation would look like A minus B would be equal to A plus JB minus C plus JD. And we would simply take the difference of our real parts. So we would have A minus C plus J, B minus D. Again, nothing particularly wild or crazy about subtraction here. Before we move on to multiplication and division, does anybody have any questions? All right, well, I'm going to interject a comment here. Some of you may have been astute enough to notice that I did not show you how to do addition or subtraction using polar form complex numbers. And the reason is doing it in polar form is quite a pain in the butt. It is much, much easier to just convert your polar form complex number into a rectangular form complex number in order to do the addition or subtraction operation. Your calculator can do it all day long, but if you were to do it by hand, it would be a huge pain. So that's why we don't even bother mentioning it. All right, let's look at multiplication now. So using the same complex numbers as before, A is equal to A plus JB, and B is equal to C plus JD. So this is where we have to get a little bit nitpicky with how we choose to represent an operation, okay? So if I'm multiplying two complex numbers, you will always see me just put those two complex numbers next to each other. I may put them in parentheses, okay? What you will never see me do is A times B like this, because that looks too much like a cross product operation, which does not exist for complex numbers. You will also never see me do a dot B, because that looks too much like a dot product operation, which does not exist for complex numbers. I also will not do a asterisk B, because that looks too much like you're taking the conjugate of A and multiplying it by complex number B. So whenever you see two complex numbers next to each other, that means multiply. So we would have A plus JB times C plus JD. And let's FOIL this out, right? So we're going to have A times C plus J, A times D, plus J, B times C, plus J squared, B times D. What is J squared?
-1.
-1. Thank you for that, Haley. So if we replace J squared with -1, we can break this down into its constituent real part and imaginary part. So the real part would be AC minus BD, and the imaginary part would be AD plus BC, like so. So multiplication of rectangular form complex numbers by hand is a little bit tedious, but it's not too terribly bad. Let's look at what would happen if we did exponential form complex numbers. So if our exponential complex number A was the magnitude of A, e to the j theta A, and our complex number B was magnitude of B, e to the j theta B, multiplying these together would look like magnitude of A, e to the j theta A, times magnitude of B, e to the j theta B. So my magnitudes would multiply. And then what happens when I multiply two exponentials together?
They add.
Exactly right. So the arguments add. So I would have j theta A plus j theta B, or simplifying, j times theta A plus theta B. So multiplying complex numbers together is a little bit easier to do in exponential form. In polar form, just jumping to the end here, A times B would look like magnitude of A, magnitude of B with an angle of theta A plus theta B. And now let's look at division. So once again, complex number A is A plus JB. Complex number B is C plus JD. And so if I want to divide A by B, I'm going to get, I'm leaving myself some room there for a reason, A plus JB divided by C plus JD. Now, there's nothing particularly wrong with this, but in every other operation dealing with rectangular form complex numbers, we have been able to identify a real part and an imaginary part of our resulting operation. Right now, we have a ratio of rectangular complex numbers, but there isn't a specific real part or imaginary part that we can point to. So in order to fix that, I'm going to multiply by a fancy representation of the number 1. And I'm going to choose to do that as B conjugate over B conjugate. So what would B conjugate be?
C minus JD.
Exactly right. Thank you. So C minus JD over C minus JD. And now effectively, I'm just doing multiplication, but I'm just doing multiplication for the numerator as well as denominator. So foiling things out here, we would have AC minus JAD plus JBC minus J squared BD divided by C squared minus JCD plus JCD minus J squared D squared. So earlier, Haley, I believe, correctly told us that J squared is simply -1. So that would look, let me just write that in here really quickly. So J squared is -1. So that's going to look like AC plus BD plus J BC minus AD divided by C squared plus D squared. So multiplying by the complex conjugate of the denominator over the complex conjugate of the denominator makes the denominator just a real number. And so now we can kind of split that out. And what we'll have is AC plus BD over C squared plus D squared plus J BC minus AD over C squared plus D squared. So we have a distinct real part and a distinct imaginary part. Performing the division operation using exponential form complex numbers, we don't have to worry about any of that sort of tomfoolery, right? So we would have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of B, e to the j theta b, and a over b is just magnitude of a e to the j theta a divided by magnitude of b e to the j theta b, or the magnitude of a over the magnitude of b e to the j theta a minus theta b. And in polar form, that's simply magnitude of a over magnitude of b with an angle theta a minus theta b. Okay, so before we move on from this, are there any questions? All right, so let's look at the in-class assignment. So for problem 1 here, you are asked simply to express each of the following complex numbers in polar form, where our angle is between negative pi and positive pi radians, or negative 180 degrees and positive 180 degrees. I need to update things really quickly here because this answer right here is in exponential form and we are told polar form, so we can just throw all those away because that's not really what we're looking for. So all I am expecting you guys to do for this particular problem is to just be able to use your calculator to convert directly from rectangular form into polar form. Okay. So I know the answer is literally right there, so we could literally just read it off. I'm going to pull up the Casio. So let me see who's in the chat really quickly, or not in the chat, but in the Zoom thing. Participants. Cameron, could you tell me what type of calculator you have?
I have a Casio 115.
So Cameron has a Casio 115. So I'm going to bring up the Casio 115. We're going to clear all this jibber jabber out, and we are going to work part A using a Casio 115. Okay. So just for sake of argument, so for part A, this is the number that we're looking at. So I'm going to type in negative 18.5 minus 26.1 engineering button. And earlier we set this calculator to give us the answer in polar form by default. So if I just press equal, I get 31.99156, so 31.992 with an angle of negative 125.329, or the exact answer that I was looking for, right? So nothing wild or crazy there. I would really appreciate it if you guys tried to do parts B and C by yourself, and then just let me know if you have any trouble, and also let me know which calculator that you're having trouble with, and I can show you how to do it. Anyone having any difficulty with parts B or C? Is there anyone opposed to me moving along to problem 2? All right. So in problem 2, we are effectively just doing the opposite, okay? So we are asked to express each of these complex numbers that are in a combination of exponential form and polar form and put them in rectangular. Baylor, what kind of calculator do you have?
TI 36.
TI 36. All right. So we're running the whole gamut here. Good deal. So we're looking at this number A, 61.2 e to the A 1.939. So let me ask you guys generally a question here. Do you see a degree symbol on that 1.939?
No.
No. So if you don't see a degree symbol, you should be assuming that that angle is in radians. So we could take the time to switch our calculator from degree mode, like it's currently in, we can see that here, to radian mode, but I am too lazy, so I'm just going to use a simple conversion. There are 180 degrees in pi radians, so if I were to put this into my calculator, I would put in, and I'm just in the habit of using parentheses, 61.2 second pi is going to pull up the complex menu. So our angle operator here is just option 1. I'm going to do another parentheses because I'm going to do some math on this angle. So we do negative 1.939, and then I'm going to multiply that by 180 over pi. So that's converting that angle that was in radians into degrees. And move my cursor over, close parentheses, and then because this calculator is set up to give me the answer in polar form, I'm going to tell it to convert by pressing second pi and then option 5. And we get negative 22.028 minus 57.098 and some change. Let's make this go away. And certainly looks like that answer. So I would like for you guys to take a moment once again and try to work parts B and C of this problem with your respective calculators. And if you have any questions about anything, I'd be happy to answer them. So I'm genuinely surprised that none of you have mentioned that you've gotten a math error working on part B.
Yeah, I have
All right. So Haley, what type of calculator do you have?
Casio 115.
The 115. Okay. So the reason why you're getting a math error is because all of these calculators are expecting complex numbers to have a positive magnitude. So the way to get around that is to trick your calculator by just doing negative and then open parentheses and then the complex number that we need to put in. So that would be, let me get to a screen so I can see it, 36.2. To get the angle operator on the Casio 115, we press, there it is, shift minus. And then we're going to put in 108 to convert this into rectangular form, shift 2, and then option 4. And we get 11.186 minus 34.428, blah, 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 I.
Is there something different about the TI? Because I didn't get an error doing it.
Let me see.
Because I just did the negative 36.2 angle 108 and then complex to A plus BI.
Okay, so the TI doesn't seem to care if you put a negative sign, a negative magnitude, but the Casios definitely do. So another reason why the TIs are better, in my opinion, for this particular thing. Yeah. I know the 115 gives you the error if you don't put the parentheses around it. I think the 991 does as well. Yep. Or at least my physical one does. All right. Anybody having issues with part C? That one should be fairly straightforward. Nothing real wild or crazy. The magnitude is positive and the angle is in degrees. So would anyone be opposed to us moving on to number 3 or problem 3? All right. So for this problem, things can be made much, much easier on us if we know how to store variables in our calculators. So let me find another random person to harass about what type of calculator they have. Leah, would you mind telling me what type of calculator you have?
TI 36.
TI 36. Thank you, ma'am. All right. So I'll pull up the TI 36. So the TI 36 is very easy to store stuff into its memory. The Casios aren't particularly difficult by any stretch of the imagination, but the TIs are a little bit easier here. So if we look at problem 3, what I'm going to do before I worry about literally anything is I'm going to take all 3 of those complex numbers, X, Y, and Z, and store them in my calculator's memory. So X is -2 plus J6. So I'm just going to do -2 plus 6I, store, and then I press the variable button once and enter. And now that number is stored in my calculator. It spit out something in polar form because it's set as polar form in default, but it is the correct number. So I'm going to do a similar thing 4 plus 7 I, and store that as y by pressing the variable button twice. Press enter. And then lastly, -6 minus 5I, store that as z by pressing the variable button 3 times. And if we look at our first operation, we are asked to simply multiply x by the sum of y and z. So I would just do x times y plus z. Enter. And I get 17.888 with an angle of -116.565. Now, you all may notice that on the correct answer, it says that the angle should be 243.435 degrees. So let's talk about that really quickly. So in the problem statement, we are specifically asked to express our answer in polar form with the angle having the smallest possible positive magnitude. So the calculator is always going to give us a result that is whose angle is between -180 degrees and +180 degrees, or something that's in, or excuse me, so that the angle will never be greater than 180 degrees. So what we can do, we know that our magnitude is right, but if we want a positive angle, I'm going to do second complex. Option 2 here is just going to give me the angle of our prior answer. And then I'm just going to add 360 degrees, excuse me, to go around the circle. And that gives us the answer, the angle that we're actually looking for. I'm going to work part B with a Casio 991. So let me open up that one. So it's going to take me a moment here, but I'm going to store all those variables. The process for storing the variables in the Casio 115 is very similar. So -2 plus 6, and then I'm going to press store A. So it's storing X as A. And the only reason I'm storing X as A is because there isn't a Z memory location on these Casios. 4 plus 7, store as B. And then -6 minus 5, I, store as C. And if we look at problem B, we are asked to do y conjugate times y times z. So in order to do that, I'm going to hit option. Oh, geez. I think option 2 is conjugate. Let me look at my calculator whose language is English. Yep. So the conjugate of B, alpha B times B times Z, which I stored as C, gives me this thing. If I change it, I get 507.666 with an angle of -140. Once again, I would just add 360 degrees to that -140. And so I can facilitate that easily by pressing the option button. The argument of my answer plus 360 is 219.806 degrees, which is what I'm looking for. I'll leave part C for you guys, but if you have any questions or issues with your calculators, please let me know and I'll tell you how to sort it out.
What do we do about the j raised to the 7th power?
So the short answer is it depends on whether or not your calculator can handle it. So for instance, I believe that this particular Casio can. So if I typed 1 and then press the engineering button and then raised it to the 7th power, it gives me this thing, which is actually just -j. But if I pull up the TI, I think it's going to freak out. I might be mistaken. Yeah, so it gives me a domain error. So it doesn't know how to interpret j to the 7th power. So let's talk about that just really quickly, right? We'll do it down here. So I'm going to make a simple table here. So let's put j to the 1st power right here. So j to the 1st power is by definition just j, which is the square root of -1, right? Well, j to the 2nd power is then just square root of -1. I don't need this one right here. That's the issue. Square root of -1 squared, which is just -1. J to the 3rd power is just j squared times j to the 1st power. So that's just going to be -j. J to the 4th power is just j squared times j squared. So that's -1 times -1 is +1. J to the 5th power, excuse me, is the same thing as j to the 4th times j to the 1, which is just j. So it simply just cycles through these things over and over and over again. So all you have to do is subtract 4 from the index to get j to the 3rd, and your calculator should be able to interpret that. And we can do the same thing if we had negatives, right? So j to the 0 is just 1. J to the -1 is just 1 over j. If we multiplied that by j over j, we would have j over -1 or -j. J to the -2 is just j to the -1 squared, which is going to be -j times -j is going to be +j squared, which is -1. J to the -3 is, j to the -1 times j to the -2. So that's -1 times -j gives us +j. J to the -4 is, I'm going to keep putting a negative sign out front that doesn't need to exist. J to the -2 times j to the -2 is -1 times -1 is +1. J to the -5 is j to the -4 times j to the -1. So that's 1 times negative j is negative j, and so on and so forth. So if you have a power that's too negative, just add 4 to it over and over and over until it's between -3 and +3, and then your calculator should be able to handle it. Are there any other questions? All right, so I know that on the syllabus it says that we are going to do a review of sinusoids today as well, but we only have 30 minutes left, and that's not quite enough time. So we'll just tack that on to what I'm going to talk about at the beginning of Monday's class meeting. So Monday will largely really just deal with sinusoids, and then we'll introduce a couple of concepts like phasors and impedances. For your homework assignment, this homework set number 18, there isn't really any problems that are jumping out at me as being particularly difficult or anything. All of this stuff should just be an exercise in learning how to use your calculator correctly and efficiently. And then I will do a better job of explaining exactly why we're going to use complex numbers in our next class meeting. So unless anybody has anything, and I think Austin, you had a question for me regarding a test problem, I will see you guys on Monday.